So looking at questions with more permutations. So let's have a look at this question 4 here. You've got 5 letters, and they're to be arranged in a line at random. So how many different sequences are possible? Well, it's going to be 5 factorial. In the first spot, it could be 1 of 5, and then the second spot, 1 of 4, 1 of 3 in the third spot, 1 of 2 in the fourth spot, and it must be the last one. So 5 factorial, 5 times 4 times 3 times 2 times 1 gives us 120. So what about looking at probabilities here now? If A is on the left and E is on the right, so consider that. So this is what it's going to look like. A's there and E's got to be there. Well, if those got to be set in those two positions, really it's only the middle 3 positions that can be rearranged. So the other 3 objects can be arranged in 3 factorial ways because A's got to be in a particular spot, E's got to be in a particular spot. So 3 factorial ways, which gives us 6, which leaves us to a probability of 6 over the total amount from part A, which was 120. So there's only 1/20th of ways where A's on the left and E's on the right. What about if A and E are on the ends? A way to consider this: A's on front and E's at the back, or the other way: E's at the back and E's on the front and A's on the back, which was the same. Every time the 3 other elements can be arranged 3 factorial ways, and that can be done twice in 2 different ways. Or you could consider it that A and E have to be in 2 spots, but they can be arranged in 2 different ways, or 2 factorial ways. So that gives us 12 ways that A and E can be on the end. As a probability, 12 over the 120 gives us the 1 on 10. So remember, the 120 is coming from the total number of sequences possible, which is the 120. So that's why it's favourable on the total amount. For part 3 here, what about if A and B are together? Well, this is similar to what we had in the last video. How do we consider a problem like this? Well, we put A and B together and consider them as one unit. So that means the other 3 elements get put together with this element, and we've got 4 elements altogether, so they can all be arranged 4 factorial ways. But then A and B can be arranged in 2 factorial ways because there's 2 elements. So 2 factorial times 4 factorial gives us the 48, so 48 over 120, or 2/5. The 3 consonants together. So what are consonants? Well, they're not vowels, and the vowels are A and E, so the B, C and D must be together. So again, what we need to consider is that put them together, and that means we've got 3 elements with the other ones that aren't part of this group. So these elements can be arranged 3 factorial ways, but then in this group there, these ones, they've just got to be together. They don't have to be in any order there. So you can have BCD or DCB, or so that can be considered 3 factorial ways because they can be organised 3 factorial ways. So 3 factorial times the 3 factorial, that can occur 36 ways. So we can get B, C and D together. So as a probability, 36 on 120, or 3 on 10. The letters are not in alphabetical order in either direction. Well, get to consider this. There's only 2 ways we can get alphabetical order: A, B, C, D, E, or you go the E, D, C, B, A. There's no other ways in going either direction that we can get alphabetical order, which basically is saying that the 5 factorial, which is the total amount of ways we can arrange those letters, all we're doing is taking away 2 of those options because it only occurs twice. So it leaves us with 118 ways that the letters are not in alphabetical order, which as a probability comes down to 59 on 60. So that's another way to look at it. Like from our total, how many ways can we just take? How many ways are there? We just take that off and get our total number of ways we can do it. Bit of like a complementary situation. The letters are either not in alphabetical order, or they are in alphabetical order. Alphabetical order only occurs twice. B, C and D occur in alphabetical order from left to right, but not necessarily in order. This one's not an easy type of problem to consider because B, C, D, this is the ways we can start to look at it. So we can either have B, C, D there, or B, C, D, B, then two other elements in the C, D, B, C, the elements there. So really I had to list out the ways to do it. Not a fun way to do it. And you can see how we can get 10 different ways of arranging B, C, D such they're in alphabetical order but not necessarily together. So only two can be together at any one particular time. What we got in that situation, that every time though, the other two elements can be, doesn't matter where they are, and they can be arranged 2 factorial ways. So 10 times 2 factorial can be 20 ways altogether that we can get that. So even though I counted up 10 here, the other two letters can be in alphabetical order. I don't have to be in any order. They can be arranged in 2 factorial ways. That gives us 20 on the 120 or 1/6. What about if C's in the middle? Well, again, if C's going to be in the middle, it's got to be in one particular spot. The others can be arranged 4 factorial ways around that. So 24 over 120 or 1/5. Well, you can think about that one in a different way as well. The idea that, well, what's the probability of C being in the middle? Well, it's got one spot out of the 5 that it has to be in. So one favourable situation out of the 5 it can be in, 1/5. So you can think of it that way as well. Both B and D have letters on either side of them, so if that's going to be the case, they've got to be in the 2nd and the 4th spot. So again, if they're going to be in those particular spots, they can be arranged 2 factorial ways in those 2 spots, and then the other letters have to be arranged in the other 3 spots around them, which can be happening 3 factorial ways. So you can see how accounting techniques allowing us to get the favourable amounts over the total amounts and giving us our problems. Now this time we want to look at the letters of the word again being arranged in random in a line. Now how many different letter patterns can we form? Now the only problem with this one is that A occurs twice. Now really when we look at it, if we swap those around, they would look exactly the same. There's no difference between these two A's, which leads us to a little bit of a problem, because if we said, well, we arrange those in a line 5 factorial ways, which would be like we had the A, B, C, D, E, but because if we swap these two around, really we're doubling up, so that's not changing if those two are swapped around in those positions. So what we've got to do is divide the 5 factorial by 2 factorial, because the A's there basically cause us to have a situation where we are doubling up or having a multiplication effect of our words that we can arrange by 2 factorial. So that's why we divide by the 2 factorial there, because we have 2 letters there that are going to be exactly the same. So we only get 60 different letter patterns. Remember, that's the key word there, different. So what the probability that A's are together? So if we got the A's together, then we can arrange those 4 factorial ways. Because again, the A's now, because they're going to be together, and they can swap over, but they're going to be the same. That's why we don't multiply that by 2 this time. So we have the 4 factorial, 24, and so we can get that in 2/5 of the time. If they're going to be separated then, well, if the idea that if they're together it was 2/5, then separated it must be 3/5, because it's a complementary event. So that's the whole idea for that one. Now, let's look at words that are a bit more complex, and see how many different ways how many different arrangements we can get these. And they don't need to be proper words. So consider the word Parramatta. Well, we've got 10 letters in the word Parramatta. So 10 letters there can be arranged 10 factorial ways. But again, we've got to consider that there's 4 A's in there, there's 2 R's and 2 T's. So if we swap the T's around, we're getting exactly the same. So we don't need to double up in that respect. Or if the A's are swapped around, then because they're exactly the same, we don't have we we're going to have a multiplication factor of 4 factorial there of for these letters, because they're going to be arranged. A's can be arranged in 4 factorial ways. So we have to divide by the 4 factorial, divide by 2 factorial, and divide by 2 factorial, because of the letters that are occurring more than once. Something like engineering, so 11 letters there, but 3 E's, 3 N's, 2 G's, and 2 I's means we have to divide by those multiplication factors. Woolloomooloo, always a favourite. So 12 letters there, but 2 O's, sorry, 8 O's and 2 L's in there, means we have to divide by 8 factorial and 2 factorial. Means what looks like it starts to be complex isn't that many different. Oh, well, we say that, I mean, it's still nearly 6,000. So Q this time has 4 boys, 4 girls in line. Now, if the boys and girls can stand anywhere, well, it's 8 factorial. So there's no problem which way the boys go and girls go. So, and think about this one, like, it's not like the last one with the words, because A's are the same, but boys and girls are different people. So that's why it's still 8 factorial. We're not dividing by multiplication factors of 4 factorial. If the boys and girl alternate, so really we go boy, girl, boy, girl, boy, girl, or girl, boy, girl, boy. So it can be looking at either of those. So really we've got to consider that boys can be arranged in 4 factorial ways, and the girls can be in particular spots, but in 4 factorial ways. But then we can swap them over. So whether we start with a boy or a girl, so there's 2 different ways we can do that, which leads us to 1152 different ways we can get boys and girls alternating. If 2 particular girls wish to stand together, well, again, treat those 2 girls as one unit. So that means altogether we could have 7 people standing in line, but those girls can be arranged in 2 factorial ways. They can be in a group that's either A's next to B or B's next to A in any particular order, so that's why it's 2 factorial. If all the boys have got to stand together, again, consider the boys as one group, and the girls doesn't matter where they are, so there's 5 factorial ways that they can all stand in a group, and the boys have got to be together, and they can be arranged in 4 factorial ways. So that's the boys being in one group with the 4 girls, and then the boys being considered in being arranged in 4 factorial ways. So what's the probability that the 3 particular people be in a queue together if the queue forms randomly? So really, well, ABC, or CBA, or CAB, or so 3 particular people. So again, we group them as one, and then we got 5 other people there. So we can combine them 6 factorial ways as when we got treated them as one group. But then in that one group, that they can be arranged. They've just got to be in a queue together. So they can be arranged 3 factorial ways. So 6 factorial times the 3 factorial. Remember we said the number of number of ways we could get that queue was 8 factorial. So there's our probability. It comes down to 3 out of 28 there. This time we've got books. 10 books are being arranged on the shelf. The books can be anywhere. It's 10 factorial ways. If one book must be first in line, or it's got to be first in line every time, then the other books can be arranged 9 factorial ways. 2 books are kept alongside each other. Well, again, treat them as one group, one pair as a group. So that can be arranged 9 factorial ways. And again, those 2 books together can be arranged 2 factorial ways, which gives us that many ways in which we can organise our books. 3 books have to be kept alongside each other. Again, we'll consider them as one group, so we're going to have 8 groups altogether. So they can be 8 units altogether. 8 elements can be arranged 8 factorial ways, and those 3 books can be arranged 3 factorial ways. So there's our total number there. In this problem, we got the letters of the word geometry being arranged in a straight line. Vowels must be in the 2nd, 4th, and 6th. Now, if you notice, there's only the three vowels, 1, 2, 3. If they've got to be in 3 particular places, they can be arranged 3 factorial ways. It means the other letters must be arranged in the other places, and there's 5 of those, so they can be arranged in 5 factorial ways. So if particular ones have to be in particular spots, that's okay. We just have to see how many ways they can be arranged, and then the others can be arranged in the other spots in a certain amount of ways. So that's how we look at some of those problems. So again, different techniques, different ways to look at problems. We need to keep in mind what the question's asking and what we need to do to satisfy those.